Hi everybody. Just now we have done with interference patterns or interference, phenomenon called interference. Now we would like to do what we call as diffraction. Alright, so diffraction is again a wave phenomenon. Normally diffractions are normally found in a light wave, sound wave, water waves and matter waves. And however, you may ask that we never found diffractions of light waves. Alright, so it is very difficult to encounter the diffractions of a light wave. The reason is that the wavelength of a diffraction, a wavelength of light is very small compared to the dimension of obstacles. Alright, so this is the reason, right? Normally when diffraction takes place is that when a light or when a wave encounters obstacles. When a wave encounters obstacles, so the phenomenon called diffraction takes place. When a sound wave encounters obstacles, it occurs, the diffraction takes place, water wave, so on, right? So we normally found a sound wave diffraction, that is, let's say, if we have walls, and if somebody is talking other side of our walls, we could able to hear the sound. All right. So the point is, where how sound could penetrate through our wall? This is not possible, right? It's not possible for sound to penetrate through our walls. What happens is that the diffraction is taking place. That is why we could able to hear sound from other side of our walls. Similarly, we have a diffractions due to water waves. Alright, so you might have seen this, right? This is the diffractions due to water wave diffractions. So I told you whenever there is obstacles, diffraction normally take place. So these are the two worlds which act as obstacles, and when a water wave encounter these two worlds, diffraction normally take place. That is a spreading of a wave taking place. You can see the spreading of wave, and this is what we call as a diffraction of a water wave. Examples of a diffraction of water wave. Another example is this. So again, these two are the obstacles. When a water waves encounter these two obstacles, you see a diffraction, spreading of a light or spreading of a water wave taking place, and this is what we call as diffraction of water waves. And now look at here. Now again, we found diffractions in a CD, right? When you might have seen a CD and you see a different colors or found on a CD. This is all because of diffractions. This is again because of diffractions. All right. So now again, so this is what we found. When a light, what exactly diffraction is? When a light has to encounter obstacles. So when a light encounters these edges, these are the edges of a states. When a light encounters the edges of these two states, you see the spreading of light take place. And the spreading of a light take place such that light enters into a shadow. This is the shadow regions. This is the shadow regions. This is the shadow regions. So therefore, this is where we found diffractions. Alright. So this is what normally we found in a day-to-day life. Whenever we have a shadow, you look at very carefully, right? When you look very carefully in case of a shadow, you find different regions of shadows. Why there is a different region of shadows, right? The different regions of the shadows are normally occurs because of what we call as diffractions. Spreading over. This is what we have. So this is the incident waveforms. This is incident waveforms. This is an incident waveforms, and this wavefront is a plane waveforms. Plane waveforms incident on a sticks, and this is obstacles, and then spreading take place. The light spreading of light take place such that now this actually is a shadow region. This actually is a shadow region. However, light could enter into a shadow regions. And how light could enter into shadow regions? Because of diffraction, because of spreading of light. Again, this is the part. This is the part. This is the this. Again, I will give you one more diagrams. This is again. This is the one part. This is other part. These are the different examples of the shadows and the different regions of shadows which occurs because of diffractions. Again, I have this. This is what we call as the sun, and this is an obstacles. All right, and normally we explain this in case of solar eclipse times, right? So look at here. Normally shadow should be around this. Why? Because light travels straight. Light travels straight, and actually this should be a shadow. This should be a complete shadow. Actually, this should be this entire region should be a complete shadow. However, you see a different regions. This is a hard shadow. This is what we call as umbra that is done in a lower class, and this is a soft shadow which called penumbra. And this umbra and penumbra regions in a shadows occurs because of diffractions. All right. So now we may wonder, right, how light would enter into these regions. We believe that light travels straight lines, and how light somehow curve and then enter into our shadow regions. And this is all because of diffractions. How spreading of light take place? A spreading take place such that light enter into shadow regions is what we call as diffraction. So this is what we have diagram. All right, and this is what we have. So the simplest definition of the diffractions or the phenomenon, the definition of diffraction was found by Isaac Newton. He said that the diffraction is nothing but the spreading of light. When a light passes through a slit or narrow hole, spreading takes place, and this spreading is because of diffractions. This spreading is what we call as diffraction. So you see, the spreading of a light taking place, and this spreading of light is what we term as diffractions. This is the spreading, diffraction is taking place. Now look at this. Look at this. The spreading of light depends on the size of slit. So if this size of slit is a little bigger, so therefore spreading is less. And this size of slit is little smaller than this. So the spreading is little more. Now, number C, the size of slit is very, very small. So spreading is much better. Diffraction is much better. So we say that normally diffraction occurs. Very beginning I told you that when a light encounters an obstacle, the size of obstacles and the wavelength should be comparable. If a size of obstacles is so big, if a slit is so big and a wavelength is so small, then we hardly observe diffraction. So the best diffraction we found number C. Alright, so this is what we have. So in a way, diffraction is a spreading of light or bending of light around a corner of obstacles. Alright, around a corner, bending of light around a corner of obstacles, so that lights enter into a shadow regions. Lights. So whenever lights encounters opaque obstacles, light undergo bendings such that light goes into shadow regions. This is what we define. So it is defined as the bending of wave around a corner of an obstacles or through an aperture into a region of geometrical shadows. Geometrical shadow of the obstacle or aperture. So this is what we define as diffractions. A simple definition is that the spreading of light. When a light passes through small slit, when a light encounter obstacles. I say this is a spreading of light when it encounter slit or obstacle, right? This is what we define as diffraction of light. So now next point is that this is again diffraction, right? So next point is that now we talk about double slit. Just now we talk about double slit. So now the question is, if I close one slit, if I close this slit, so what we are going to get? What kind of change are we going to observe? If in the case of Young double slit experiments, if we close one of the slit, all right, so we are left with only one slit. And what are we going to observe? What change we are going to observe? Alright, so this is what we are going to see. This is what we are going to see. When a double slit in a Young experiment is replaced by a single narrow slit illuminated by a monochromatic light, while it was single wavelength. That should be very important, right? So what we are going to see? We are going to see diffraction patterns. We are going to see diffraction. This is what we call as diffraction patterns. We are going to see diffraction patterns. What exactly is that diffraction patterns? And diffraction pattern is the pattern where you get broad central bright. This is going to be a broad central bright. This is going to be a broad central bright. Then as you go up, or as you go this side, as you go that side, you see the maxima or the brightness goes on decreasing as you go away from central bright. So this is a very different from interference pattern. In case of interference patterns, the fringes are equally spaced. However, in this case, the fringes are not equally spaced. The central bright is very bright. And is what we call the broad central bright, and as you go away from either side of this central bright, you see the bright fringe, the intensity of bright fringe goes on decreasing. Alright, so now what we are going to do is we are going to find out the intensity of a central bright. Alright, and then what we are going to find is we are going to find out the position of first secondary bright, second secondary bright. This is how we are going to do it. So this is what we are going to do. So this is what we observe when we remove one slit. When we remove one slit of a double slit experiments, we are going to get this. Maybe an example they may ask, right? So this is what we have. Single slit diffractions. Single slit diffractions. So look at here. This is the slit. I have a slit. Let's say a slit, single slit LN size. What is the size? Size is, let's say, A. A is the size of slit. A is the size of slit. A is the size of slit. I say at any point on a screen, let's say at any point on a screen, at any arbitrary point on a screen, at any point on a screens, let's say point P, path difference would be equal to LP NP minus LP. Path difference is going to be A sine theta. Why? Because this is theta. This is theta, and this angle is going to be theta. So this is the path difference. This is the path difference. This is the path difference. What is this? This path difference is going to be A sine theta. This is the sine. Alright, so this is going to be theta. Why? Because this angle is going to be theta. So therefore, this is going to be a sine theta. So I say at any point on a screen, point P, at any point P on a screen, let's say at any point P on a screens, path difference is this. So I said for small theta, so NP minus LP is going to be A theta. This is the path difference. This is the path difference at any points. This is the A is the size of state. A is the size of state. Now look at here. Central point C. C is the center of center lights on our screens. C is the central right. So since the C is the centers, so path difference would be equal to C is the center, right? Let's say C is the center. C is the centers. Since the C is the center, I say light incident on this is I have a plane wavefront incident on the states, and since the C is the center, and then the path difference would be equal to what? Would be 0. If it is a 0 path difference, then it is a constructive interference. This is constructive. This is a constructive interference, right? This is a constructive interference, which means that all the part of the state, all the part of a states are in phase at center C. Alright, this is very important. So let's say I'll write like this. This is much better. Alright, so I have this center. This is screen and see all the lights. Path difference is 0. That means all the parts of the states are in phase at point C. Therefore it is constructive, and therefore C is what we call as a broad center bright. Broad center brights, and it is the maximum. This is what we call as a central maximum. This is going to be a central maximum, and where we get peak. This is a central maximum. This is what we get, a central maximum. So this is the point. Why? Because when we talk about the diffractions, again one very important concept is every part of a state act as a source. Every part of a state act as a source, and then since this is a center, this is of a one wavefront. This could be a one wavefront. Every part of a state act as a source. Therefore, every light coming from the slits are in phase, alright, with each other when a light falls on C. Alright, every light from states when falling on a C's are in phase to each other. Therefore, we got this as a central bright. I am going to write this is again central bright, and we say we got it as a broad central bright. Why? Because the width is much bigger than the rest of secondary maxima. This we will discuss now. All right. Now this is for a central bright. Now what about the secondary maxima? What about the position of secondary maxima? What about the secondary maxima? This is what we are going to do. What about the secondary maxima? And look at here, as far as the diffraction is concerned, we can't derive the secondary condition for a secondary maxima as we did in case of interface. Why? Because this is beyond our scope. So therefore, what we are going to do is, first I'm going to give you a condition, and then later we will prove it. So condition for a secondary maxima is angular position. Let's say angular position of secondary maxima. Secondary maxima and secondary maxima, right? Secondary maxima means plural of maximum, right? Angular position of secondary maxima is given by, and this is where this is lambda is a wavelength, and A is the size of a state. This is the size of state, and where n is equal to 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4, so on. This is the angular position of this is an angular position of secondary maxima. All right. This is an angular position of secondary maxima. And then, what about this, right? Again, I say that angular position of a secondary minima is given by, and then later we will prove you, right? I will prove you, right? Angular position of secondary minima would be, alright, this is going to be, n is going to be 1, let's say this is 0, 1, right, plus minus 1, plus minus 2, plus minus 3, plus minus 4, goes on. Alright, this is what we have, angular position of this, angular position of secondary minima, angular position of secondary maxima, right? So now, how to prove that? Alright, how to prove that? I'm going to do here. Before that, let me have this, right? So, this is what we have. This is a central bright. This is what we call a central bright bands, and intensity goes on decreasing, and we will find out why intensity goes on decreasing. Why we have a maximum intensity at the center, we will discuss now. Alright, this is what we have gotten, and this is what we get, right? And this is what we are going to prove now. Alright. Alright, now let me say, to find out the central position of central maxima, right? To find out position, right? Find out position of central maxima, position of secondary maxima, Look at here. What is the how I'm going to do is, I have a state like this. This is the state. I just magnify the state, and I divide the state into a 3 equal part. Right, this is going to be M, this is going to be L, this is N, M1, M2, and this is the screens, and this is the angle, right? This is theta and this is theta and this is theta and this is theta and let's say this is the first theta 1. Let's say theta 1. I'll write theta 1. First, I will find out for first secondary maxima. To find out the first secondary maxima, we divide the state into a 3 equal half. To find out the first secondary, this is not very important for examination point of view. In exam, this is sufficient. But for your understanding, I am doing this, and your textbook, our textbook has done a very nice job to understand how the central the secondary maxima decreases as you go away from central max. This is how we are going to do it. And this is angular position of first secondary maxima. To obtain the angular position of first secondary maxima, we divide the slit into a 3 equal half. This is going to be like this, this is going to be like this, this is going to be like this. Alright. And then what we do is that I'm going to take a light between a 2/3. Take a 2/3. Take 2/3 of slit. When I take a 2/3 of a slit, I take a 2/3 of slit, and then what is the path difference between the 2/3 of slit? Path difference, I just write here. Path difference for 2/3 of slit, 2/3 of slit would be equal to, what is the path difference? A 2/3 A theta 1. And I'm going to substitute the value of theta 1. What is theta 1? If I put theta is 1, and then if theta is 1, then this is going to be 1 plus half lambda by A. This is going to be 3/2 lambda by A. And this is going to be 2/3 A multiplied by 3/2 lambda A. A cancel out, 2 to cancel out, 3 to cancel out. So path difference would be equal to lambda. This is what we have. So these two lights interferes on the screens and constructing. These two lights interfere constructively. These two lights interfere constructively. Alright. However, now question is that, however, these two lights, if this path difference is lambda, and that path difference must be equal to lambda by 2. If this two path difference is lambda, then that two path difference must be equal to lambda by 2. Therefore, these two lights interfere distantly. This is going to be constructively, and these two destructively. Alright. So therefore, look at here, therefore, out of entire state, 1/3 is for 1/3 contribute, or 1/3 interfere constructively, 1/3 interfere constructively, and I got this. And 2/3 interfere destructively. Therefore, I say at point P, this point P, you'll be getting a 1/3 constructively and a 2/3 destructively. Therefore, the brightness is going to be 1/3 of central maximum. So, therefore, first position is that, so angle theta 1 is equal to lambda by A plus minus, you get 1/3 of central bright. 1/3 of central bright. Why? Because we say that 1/3 part of slit contribute constructively, and a 2/3 part of a slit doesn't contribute, right? Therefore, the brightness is going to be 1/3. All right. Now for what about this one? The secondary minima. What about the secondary minima? Again, same concept I'm going to use. I divide the slit into 5 equal parts. I divide the slit into a 5 equal parts. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Alright. And again I say these two are constructively, and I say path difference will be equal to, again What is the path difference? Path difference would be equal to 4 feet a theta 2, and what is theta 2? Theta 2 is going to be 4 by theta 2 is going to be 5 by 2, lambda by a, 5 cancel out, path difference is going to be 2 lambda. Right. Again, these two are constructively. Alright. Again, we say that 1/3, 1/5 in contribute. I mean, 1/5 is what we call as interfere constructively. Interfere constructively. And 4/5 interfere destructively. So therefore the brightness goes to 1/5. So on. Therefore my conclusion here is for secondary maxima, the angular positions, my conclusion here is angular positions are what we call as n plus this lambda by a, where n is equal to plus minus 1, plus minus 2, plus minus 3, and the brightness of secondary maximas, would be 1/3, 1/5 and 1/7, so on, of each central maxima. This is what we have. So therefore brightness goes on decreasing. Why brightness goes on decreasing? The contribution to the maxima would decreases as you go higher and higher and higher. Alright, first is going to be 1/3. The central is going to be entire part. The entire part of all the part of a slit contribute constructively. Now in case of the first secondary maxima, 1/3 contribute constructively. Then a second secondary maxima is going to be 1/5 contribute constructively. This is how it goes. This is for secondary maxima, position of secondary maxima. Alright, now let's move to position of secondary minima. Alright, let's move to position of secondary minima. So how to get the position of secondary minima? Again, I use the same concept. In case of a first secondary minima, or a minima, I divide the slit into a two half. So what I'm going to do is what we have. This is going to be A by 2, this is going to be A by 2, and this is the point P. And now look at here, what is the path difference? This path difference is going to be what? This interfere with this, right? This path difference is going to be A by 2 theta 1. This is destructively, right? And what is theta 1? Theta 1, this is theta 1, right? Theta 1 is going to be lambda by A. So therefore, what is the path difference? Path difference is going to be lambda by A, cancel out. Alright. So this tells that the path difference is lambda by 2. This means that all the part of a slit interfere destructively. So therefore this is what means. So this destructively and this destructively goes on like this. Alright. So this corresponding to this corresponding to that, this corresponding to that. This is how interface are there. This is what we have. Now what about in case of a second secondary minima? What about in case of a second position of a secondary minima? Second secondary minima is that divide this thing into a 4 equal half, 4 equal half, 4 equal half, 4 equal part. One, two, three, 1, 2, 3, 4. Yes. And what I'm going to do is, this is some point B on the screens. Path difference, what is the path between these two? Path between these two is going to be A by 4. Alright. And then this is theta 1, theta 2, right? What is theta 2? Theta 2 is going to be theta 2 is going to be 2 lambda by A. This is the condition, right? So therefore what I am going to do is A by 4, 2 lambda by A cancel out, and finally we get, yeah. So this is again, lambda by 2 is destructive interference. Lambda by 2 is what we call destructive interference. So therefore this is what we have. So this tells us that the position of secondary maximas are given by this formula, and the position of secondary minimas are given by this formula. For secondary maxima, the brightness goes on decreasing as you go away from central bright. How brightness goes on decreasing? 1/3, 1/5, 1/7, right? As you go away from central maxima, then the brightness is going to goes on decreasing, right? So this is one part. So this is what we have. So let me write down. Maybe this has here. Let me write down diffraction pattern, right? This is a diffraction pattern, right? This is a diffraction pattern. So this is going to be our central maxima. What is this position? This position is going to be lambda by A. What is this position? This position is going to be 3 by 2 lambda by A. This position is 2 lambda by A. This position is equal to 5 lambda by A. These are the positions, central right. And what is this position? Minus lambda by A, minus 3 by 2 lambda by A, minus 2 lambda by A, minus 5 by 2 lambda by A. These are the positions. And this is a central bright. I call this as a broad central bright. This is what we call as a broad central bright. And now look at here, unlike fringe width, in case of interference, when we talk about interference fringe width, this is equal to lambda d by small d. This is equal, I say it is equally spaced for interference. Equally spaced. This is equally spaced in case of interference. What about diffraction? Look at here. So the fringe width of a central broad bright is fringe width of central bright would be equal to that angular width. I am talking about angular width. Angular width would be, what is that? Lambda by A minus lambda by A. This is equal to 2 lambda by A. This is a fringe width. And what about the fringe width of a secondary? Alright? So fringe width, I'm sorry, this is missing here. Fringe width of a secondary maxima or minima, whatever, right? Minima, maxima. So this between these two, right? So this is going to be between these two. Therefore, this is going to be lambda 2 lambda by A minus lambda by A, and this is going to be lambda by A. This is, so therefore the second bright is going to be much bigger, twice of secondary maxima. So this is, so therefore unlike interference patterns, the brightness is not, the width of a central bright or width of a bright or dark, width of a fringe are not equally spaced. So that, and this is what I am going to show you now here. This is the wave pattern of diffractions fringe. Alright, now I will show you a geometrical, I will show you a picture. This is what we have. This is much broader, and as you go away, then this becomes thinner, right? This is what we have. This is what we have. Alright. Here, B refers to a size of slit. B is nothing but A. Here, B is nothing but A. And look at here. This is a central bright and twice of secondary. This is the width of secondary. This is the width of secondary maxima. Width of secondary maximas. And this is the width of central bright, and this dark bright, dark bright. So this pattern you are going to see. Alright, now last part I would like to do is a double slit diffractions. Double slit diffractions. So when you have a double slit diffractions, the difference is that in case of a single slits, you are getting only a broad peak, and as you go away, then peak becomes smaller and smaller. However, when you do a double slit diffraction pattern, you are getting this. This is the double slit diffraction patterns. You will be getting a broad central bright. Within the broad central bright, you will be getting interference. This is the broad peak, and this is going to be a interference patterns. This is what you are going to get it. So now we would like to say that the number of this interference pattern in a broad peak is determined by two factors. That is A is the size of slit, size of a two slit, and D is the distance between a two slit, right? So this is given by, the number is given by, this number is given by ratio of these two. Alright, ratio of these two. So this is what we have. So if A is extremely very small, then the number of the interference fringe in a broad peak is going to be large number. So therefore this peak appears flat, and this is where we found in case of interference fringe. This is what we have. So the number of interference fringe occurring in a broad diffraction peak depend on a ratio that is A by D by A. For small a, the limit, or I say A goes to very small, if A is very, very small. If A is very, very small, the diffraction pattern will become a flat and will absorb a double slit interference fringe. Double slit interference patterns. So the condition to get a double slit interference pattern is this should be maintained. This ratio should be maintained. So this is one very, very important. And this is last. I have this. This is how you have how you differentiate double slit and single slit diffraction. This is the single slit diffractions, and this is what we call as single slit or double slit diffractions, right? So with this we come to an end of a diffraction also, and the next class I would like to discuss the difference between a diffraction and interference. Okay, thank you.